My name is Josh Gordon. I work on the Tensorflow team at Google, and I teach deep learning at night at a couple universities in New York, Columbia, and Pace. And it's really fun. Anyway, I hope you can see my screen. We have 3 talks today. Mine is introductory, and I'll just give a quick overview of a neural network. And then my friend Gus will follow up after that with some TensorFlow code using TensorFlow Hub, which is a really easy and effective way to do transfer learning in practice. And he'll show you models like BERT. And then my friend Wolf will follow up later today with some lower level code in a great talk called TensorFlow from the ground up, so you can understand how things work under the hood. I have a lot of slides, so if you have anything that you'd like to know about in particular, feel free to put it in the chat. I can bounce to that section. But my plan will basically be to give you a quick overview of neural networks for folks who are new to it. So this is basically what we'll cover. What is deep learning and how does it fit into the machine learning spectrum? And then we'll take a look at what a neural network is, and we'll move from a cartoon neural network, and then we'll zoom in on neurons so you can see a little bit more about what they actually mean. And then we'll take a look at different families of popular neural networks, things like CNNs, RNNs, DNNs, transformers, whatever, just so you can get an overview of the different models that are available. And then I have some good educational resources for you at the end. So anyway, this is a diagram that I borrowed from one of the 2 books that I'll recommend. It's by Ian Goodfellow, and this is the free academic textbook. And the other one will be a practical book that you can use to get some coding experience. But anyway, this is a broad overview of the machine learning spectrum. The outermost circle, and the reason I'm showing you this is that there's a lot of terminology in ML, and I just wanted to break it down a little bit. So the outermost circle is AI, and this is this very broad general field that's been around for a very long time. And the way to do AI research is basically think of a problem that people are good at, but computers are bad at, and solve it in any way you like using any technology you like. And that can include something like a rule-based reasoning system, or it could include like a minimax tree search if you're playing a game of chess, or whatever you like. Zooming in a little bit, you have machine learning. And machine learning is a fancy way of saying programming with data. You can think of it as using, or programming with statistics. And machine learning has been around for many, many, many years. And many machine learning models are a lot simpler than they sound. So something like linear regression would now be considered machine learning. And you might have covered that in high school if you ever were trying to find the best fit line, and maybe you had a model like y equals mx plus b. Now that's in the machine learning spectrum. And the reason it's in the machine learning spectrum is you have some model, y equals mx plus b, with some parameters, the slope and the intercept, and you're adjusting the parameters based on data. You also have popular models like things like decision trees and k-nearest neighbors and stuff like that. Moving in, we get into this area called representation learning. And this is where things like neural networks start to take off. And I'll show you what that means in a moment. The basic idea is that prior to neural networks, you would spend lots and lots of time doing something called feature engineering. And so you would have a very simple model, like a decision tree or a linear classifier, and you would write lots of Python scripts to come up with really solid features. And you would feed those features into the model, and it would make a decision for you. What's really amazing is neural networks do automatic feature engineering. They start from very simple features, and they learn a representation of the data automatically. And that's made them incredibly successful. So this is the cartoon neural network that I'll break down. At the top, we're looking at an input layer. And what the squares represent, you can imagine that maybe these are the pixels from an image. So maybe we have a grayscale image, maybe it's of a cat or a dog, and we're trying to classify it. And basically the pixels are fed through these circles, and each circle here corresponds to a neuron. Each row of circles corresponds to something called a layer. And these are fully connected layers. The little gray lines are indicating that every every input is connected to every neuron. We have 3 layers here of weights. So this would be a deep neural network. And the very last layer gives the output classes. And here, we have maybe 9 outputs. So this would be a 9-way classifier. It could be a cat, a dog, a flower, or what have you. And let's take a look at what this does and how it works. The basic idea of deep learning is that every layer learns a new representation of the data. So for example, we're starting with the raw pixels. The neurons in the first layer are receiving these raw pixels, and they're learning a weighted combination of the pixel values. So what that could mean is that this neuron is capable of detecting combinations of pixels, and that could be something maybe like an edge or a simple line. The next layer no longer sees the pixels. Instead, it's seeing the features that have been emitted by the first layer. So the second layer is now maybe receiving a bunch of lines and edges, and it learns combinations of those edges, which could be a simple shape. And then you can imagine if you have another layer, it's learning combinations of shapes, which could be a simple texture. And what that means is by the time you get to the output layer, instead of thinking about your problem in terms of the pixels, it's thinking about it in terms of these high-level features, which actually can get really abstract, and it makes it much easier to classify the data. And what's really cool, there's historically, if you go back like 8 years, it was much easier to train a neural network to classify the data than it was to understand exactly what's happening inside the network. And this is a visualization from a really great website, which I encourage you to check out. It's called distill.pub. And it's a piece of work that's trying to visualize representative patterns that are detected by each of the layers and by the neurons in the layers. And you can see on the left here, this is some early layer in a neural network. It's learning to detect edges. And as you move, thank you for the link. And as you move up, you see that layers are detecting textures and then eventually patterns, different parts, and then actually objects that have like some semantic representations. And this would be from a very deep neural network trained on a whole lot of data. But it can be really beautiful and quite trippy. So basically, deep learning is representation learning. And the reason neural networks are so effective for things like image classification is that you can start with raw data, the pixels from an image, feed it through a network, the layers will learn features, and that allows it to effectively classify the data. And this is in contrast to all other machine learning models, things like decision trees or support vector machines or logistic regression or whatever, when you have to manually come up with sophisticated features in order for the model to be successful. Anyway, there's different terminology here. You can look at the width of the layer. And roughly, like the wider your layers are, the more types of patterns you can detect at that layer. And the depth of the network would enable you to learn a more complex feature hierarchy. It can be a little difficult to get intuition for how these networks work. What I wanted to do is just to zoom in a little bit to show you what's happening inside a neuron. And so let's take a look at a single neuron. And by the way, this slide I borrowed from two really great teachers at MIT, Alex and Ava, and they have a really good class called Intro to Deep Learning. It's freely available online. They've got a bunch of great video lectures. It's great. And they use TensorFlow as well. So I believe the website is something like Intro to Deep Learning. And I'll find a link for you after this talk. Anyway, let's take a look at a single neuron. So basically, on the left, we have some X's, and these could be the inputs to the model. And you can imagine that these will assume pixel values. And then we have some thetas, and these could be learned weights. And basically, in the neural network, the weights begin life as small random values, and we adjust them over time using gradient descent. What a single neuron does is it takes a linear combination of the inputs and the weights, and so basically we have some number. And this number could be between negative infinity and positive infinity. And right now, with a single neuron, we could say this is a binary classifier. If the number is greater than 0, we're looking at a cat, and if it's less than 0, we're looking at a dog. And oftentimes, you want something that looks more like a probability. And so you can apply things like activation functions on top of the neuron. And you could do something like a sigmoid, which would just squash that number to be between 0 and 1. And now you have a probability-like number that tells you if you have a cat or a dog. And there's different ways that you can write out what these neurons are doing. I just wanted to add some math to the slide, depending on which style you prefer. But basically, a neuron is doing a linear combination of the weights and the inputs, and it's usually squashing it to be between some range. That's all it's doing. And here's another way of looking at exactly what a neuron is doing. And I want to show you how we go from these little simple neurons to a cartoon neural network. And if you look at the top right corner of the slide, I know it's a little hard to see. We're going to build up to a little small neural network. So this is a single neuron. And you can imagine on the left here, we have some image that we're trying to classify. And as a toy example, this little image maybe has 4 pixels. And you can see the pixel values written here. Neurons only take arrays as input, or vectors as input. So usually what we do is if we have an image, we might unroll it, or we could flatten it out. So if you look at this X here, this column, this could be the input to the neuron. And we've just unrolled the pixels and lined them up. And then we have some weights, and neurons have a bias. And to compute the output, we just multiply each weight by the input, sum that up, add the bias, and that gives us a score. So that's just a visual diagram of what a neuron's doing. And whoops, let's take a look at this. So if you look at the top right, I want to go from a single neuron to something that looks more like a layer. And so now we have 2 outputs. And what's cool is to have 2 outputs. What we're doing is we're adding a second layer of weights. So now we're doing a matrix multiply. And we still have the single image, but in a matrix multiply, we're computing scores for both of the outputs at the same time. And one of the reasons that GPUs have become so popular is that neural networks use a lot of matrix multiplies under the hood. And GPUs are extremely good at multiplying matrices, and so they're really a natural fit for training models. And if you continue to add neurons to this layer, you'll still be doing a single matrix multiply, and you'll have something that looks more like a dense layer. So, and this is a really common building block in neural networks. Another thing you can do too with matrices is, if you like, you can classify 2 images or many images at the same time. So what you can do is you can have a matrix of inputs. So you can have 2 images side by side, and you can still do a single matrix multiply. And now you can get scores for multiple images at the same time. And this is another way that you can make these things more efficient. So the takeaway from this is that a single layer is a matrix multiply. If you have just a single layer like this, then you can think of this as doing basically multi-class logistic regression. So a single dense layer is classifying maybe an image into a certain number of classes. And here's what the code for something like this looks like in TensorFlow. So here we're creating a model called sequential. And a sequential model is the simplest type of model we have, and that's a stack of layers. And what we're doing is we're adding a single dense layer with 10 neurons or 10 outputs, and we have an activation function. And here, Softmax, there's different activation functions, but Softmax is a really handy one, and it basically squashes the output of all the neurons into a probability distribution. So every single neuron is between 0 and 1, and they sum to 1. And this is just a nice activation function for classifiers. So that's a single dense layer. And to create a neural network, what you'll do is add just 1 more layer. And so this is a neural network. And with the math on the bottom, you can see that each layer is doing a matrix multiply. And so we just have a second layer of neurons and weights, and now we have a neural network. Easier said than done. What's interesting is that, and this is true of basically all deep learning frameworks, you'll find that the code is relatively concise. And that's because there's lots of high-level APIs and stuff like that. So you can write the code for these neural networks in 5 or 10 lines or whatever, but it typically takes about a semester to understand all the concepts that are going on underneath. So no one, if you're new to this, you should never look at this and be like, oh, I should understand this right now. Even at MIT, this stuff takes a long time. Anyway, the other reason it takes a long time is neural networks are extremely effective, but they're also the least intuitive type of machine learning model. If you have something like a decision tree, you can literally display the tree and understand exactly what it does. but I don't really think there's anyone on the planet who can look at a neural network and have really solid intuition for exactly what's happening under the hood. It's just too complicated. Anyway, when you have multiple layers, you need to add something called an activation function. And I briefly want to show you why. And there's different activation functions. There's things like sigmoid, and there's things like ReLU. And here in the equation, you can see that the first layer is a matrix multiply followed by softmax. That's just, there's no learnable parameters there. It just squashes it into a distribution. When we add the second layer, what we're doing is we have the output of the first layer multiplied by an activation function. Another way of saying this is nonlinearity, followed by another matrix multiplier for the second layer of weights. And the reason we need this activation function is because if you're multiplying a series of matrices, that can be reduced. It's been a long time since I took linear algebra, but that can be reduced into a single matrix multiply. And we need to add a nonlinearity there so each layer can learn something different. Otherwise, the neural network won't work. And I just wanted to show you what an activation function looks like. Here it's represented by G. And we apply it before we do the matrix multiply for the second layer of weights. And there's a whole box of these. A really common one that was used in the early stages, the early days of deep learning, was a sigmoid. And sigmoids are really, really natural. Yes.
Sorry, there's a quick question in the chat. What does it mean to squash them into distributions?
Thank you. Thank you. So that's a good question. So basically, if we did not have this activation function, softmax, let's say that we have this single dense layer, and our goal, there are 9 outputs, which means that we have some input image, and we're doing, it's going to give us numbers that represent how strongly the network thinks it's one of 9 things. So like a cat, a dog, a flower, a horse, and so on and so forth. Without an activation function, all of the numbers on these neurons range between -infinity and +infinity. And just for convenience, so they're easier for us to interpret, instead of those unbounded numbers, we would like them all to range between 0 and 1. And so what an activation function does is it takes some number, and when I say squash, I mean take this arbitrary number and squash it to be between 0 and 1. And that's what I mean by squash. And that's what something like a sigmoid would do. There's another activation function called the softmax, and that's applied to the entire layer at a time. And it basically means that all of the outputs individually are between 0 and 1, but they sum to 1. So it looks like a probability distribution. And that's what I mean by squash. Actually, I know this is really small and hard to see. I should have blown this up. Basically, if you look, I can barely see this myself, but this is a little diagram of an activation function that's squashing some numbers. So this is sigmoid, and it's drawn here in blue. And the equation, which is tiny for sigmoid, is here. Basically, it takes some number, and it forces it to be between 0 and 1, and which looks like a probability. So this was used a lot in the early days of deep learning, but the issue, which we're not going to go into today, is that we train these neural networks using gradient descent. And the problem is, if you look at the derivative of sigmoid, it tends to flatten out. So it becomes very flat when you have large inputs. And basically that means when you're training a neural network, it's very difficult to get a signal that lets you adjust the weights. And it's called the vanishing gradient problem. And so basically it causes problems for gradient descent. So there's other activation functions which are used today, things like ReLU, which look a little strange and a little simpler, but they work better in practice. But basically what activation functions do is they enable the layers to learn nonlinearities. So like if you have like a problem when you have this like blue circle and this red circle, without an activation function, a neural network can't learn the curve. But with an activation function like sigmoid or ReLU, it can. So you always have them between layers. And I just wanted to show you a simple example of applying like an activation function to the output of a layer. So without the activation function, and maybe this will help with your question, you have some scores that are coming out based on how strongly the model thinks the image corresponds to each class. And when you apply the activation function, there's no learning happening there. You're just adjusting the scores. So anyway, that's just a thing to be aware of. I'm going to skip this for time. And then a deep neural network, we just continue this pattern. So you continue adding layers. And typically, typically the very last layer will have something like a softmax. So it gives you numbers that you can interpret. So here's a good question. Let me write a question on my slides and then say it's a good question. But a common question is, when should you use neural networks? And broadly, there's two types of data. There's structured data, and another word for structured data is tabular data. And this is basically any kind of data you would represent in a spreadsheet. And typically, you have like a small number of features that you and I as people can reason about and understand. So an example might be, you're trying to predict a patient's risk of heart disease. And you have some features like their height, their weight, their blood pressure, maybe like a yes/no column, like have they had a heart problem in the past, maybe yes/no columns for the different medications they're on. And this is something that you could show to a doctor, and she could look at it and say like, yes, I think this patient's at risk, or no, they're not. So that's tabular data or structured data. There's another type of data where you have a very large number of features that are hard to understand. And a good example of this would be just a picture, like of a cat or a dog. The features you have are the raw pixel values. And if you and I, we can look at the picture and say it's a cat. But if instead the computer can only see the pixel values, and if I showed you just the raw pixel values, there's no way that you could say, I think this is a cat based on this feature value. And neural networks are really, really effective when you have this high-dimensional unstructured data, because they learn representations that let them classify things like images. And this is how your workflow changes when you're using deep learning. So most of it's the same. Most of your time goes into finding the problem and collecting lots of data. But you're saved from doing all this work of feature extraction, because that's what neural networks do automatically for you. And this is totally transformative, and it saves you hours, and it means that you can apply machine learning to problems that were previously basically impossible. And I wanted to throw out one important point. If you've heard of something called Kaggle, it's a data science competition website. And although neural networks are extremely cool, something like about half of Kaggle competitions are still won using things like decision forests, or basically tree-based models. And the reason is that when you have tabular data or structured data, tree-based models are extremely effective. Neural networks really shine on things like images and text and sound. Let's see. Let me actually come back to this section, because I want to show you some different families of neural networks and things you can do with them. And before I get into this, by the way, I just wanted to mention that although the code is although understanding how neural networks work can take a long time, and writing the code can be very difficult, the core skills that you need to succeed with deep learning are also non-technical. So the truth is, most of your time, and these are just some like arbitrary numbers, where are you going to spend your time, and where is the impact when you're trying to apply machine learning to a problem? So most of your time goes into really thinking carefully about, what are you trying to do, and how are you going to evaluate it? How do you test it? How do you know that it works? How do you collect all the data that you need? And once you've done a good job on that problem, actually building the model becomes relatively straightforward. And a really good example of this, and this is slightly out of date now, but the most heavily cited paper in JAMA, and this was the Journal of the American Medical Association over like the last 3 years, was a wonderful piece of work by Lily Peng's group. She's a researcher at Google, and she was applying deep learning to basically detect diseased retinas. And what her group did is they took a model that already existed, a computer vision model, and they very, very carefully applied it to the medical domain. So the contribution that her group made was not doing pure computer vision work, but it was a really thoughtful application, and it had a huge amount of value. And I would encourage you to think about that when you're trying to apply deep learning to problems that you care about. So you don't always need to do computer vision research and come up with a new fancy model. You can use relatively off-the-shelf technology in a thoughtful way, and you can have a lot of impact. Anyway, I'll try and talk for maybe another 10 minutes, then we can take questions. So here's some different families of neural networks. Oh, I see a question in the chat. Thank you for adding that. Just one sec, let me read it. So good question. So how feasible is it for individuals without access to powerful compute resources to build robust neural networks without transfer learning? And the answer is very, very feasible. So the truth is, I think the importance of massive compute is overstated if you're not, sorry, I'm still waking up a little bit. There are lots of different problems that you can apply deep learning to. And if you're trying to train like, you know, the world's largest language model, or you're trying to train like a computer vision model with, you know, 10 million images and thousands of output classes, then yes, you need enormous compute. But the truth is you can do a lot of deep learning in practice for free with any GPU. And Gus will show you this. Google Research has a wonderful thing called Collaboratory. And you'll see this later today. It's awesome. It's a free Jupyter notebook that runs in the cloud. And what I really like about it is it comes with a free GPU. And this is great for interactive use. It's pretty much good for everything short of computer vision research. But there's a paid plan too that will give you, which is relatively inexpensive, that will give you fast compute. But you can do a whole lot with just something running in a browser or any old GPU. So totally feasible. Anyway, this is the first family of neural networks that you've seen in the cartoon. We call them DNNs, and these could be just series of dense layers. And these are the most generic type of model. Some vector goes in, you have some dense layers that classify it, you get a prediction, and you adjust the parameters of the network based on how closely the prediction matches the output that you wanted. And dense neural networks are really good when you have something like tabular data. And I tried to link to different examples on the website for each of these categories. So although tree-based models are really the best for tabular data, you can do that with neural networks too. And an example of tabular data, this is you're trying to predict, I guess, how many miles per gallon a car gets based on like its horsepower and weight. And another classic example of tabular data would be like housing prices. Like what's the price of a house in Cambridge based on the distance from MIT and maybe the square footage and the number of bathrooms or something like that. Another really popular family of models is called convolutional neural networks. And these are especially good for classifying things like images. We don't have time to go into convolution today, but it's another type of layer in neural networks that you can use. And it's especially good for images. So you'll hear things like convolutional neural networks a lot. And I just wanted to show you that here's code for a convolutional neural network. And you can see that there's these different types of layers. Again, this is super fast. It takes a long time to learn this stuff, but just so you've seen it. So you can add convolutional layers and pooling layers. And oftentimes a pattern that you'll see in these neural networks is whenever you're doing classification, the last layer is usually a dense layer. And there's that word softmax again. And what happens over time is that you begin to understand how the individual layers work. And then after a semester or so, you can look at something like this and you'll have a better sense of exactly what it's doing. Something that Gus will talk about is transfer learning. And basically, man, I have so much to talk about. It's hard to pack all this stuff into a short talk. Anyway, there's a lot of different ways to train models. And one way to train a model is to start from scratch. You start with a model with randomly initialized weights, and maybe you train an image classifier based on a lot of images. Another thing you can do too is something called transfer learning. And the idea in transfer learning is you reuse an existing model and you lightly modify it to classify new objects. And here's the basic idea if I go back a slide. So imagine this is some convolutional neural network. And what's happening here is the upper orange box has the convolutional layers. And this is what's doing, when I was talking earlier in the talk, the early layers are learning things like edges and shapes and textures. When you train this model, that's what's happening inside the convolutional layers. The very last layer is a dense layer, and that's actually classifying the data based on the features learned by the convolutional layers. And what you can do, because oftentimes those features are general, like images have shapes and textures, you can do surgery on the network. And if your goal is you have an existing model, and now you'd like to train it to classify new objects, what you can do is you can keep the convolutional layers, because your hypothesis is that those features might be useful on new images. You can delete the dense layer, add a new dense layer yourself, and train just the dense layer. And that's what's happening here. So you keep the convolutional base, you delete the dense layer, you add a new dense layer for your classes, and you train just that. And so transfer learning can be a way to quickly train models on new types of data. Another important family of neural networks are things like recurrent neural networks. And these are really, really good for doing sequence classification. So, so far we've talked about like a picture or a vector, but you might have a sequence, and a sequence could be something like a sentence where the elements can be characters or words, or a sequence could be, like a time series. And recurrent neural networks are a special type of network that are great for sequence data. And they can do simple things like text classification. They can do really fun things like text generation. And by the way, just so you don't have to type in all of these links, I know it's recorded, but you can find, if you go to tensorflow.org/tutorials, you can find all of these examples in these different sections here. And we have tutorials that show you how to apply networks to all sorts of different types of problems, different things in image classification, text classification, audio, structured data. There's all sorts of really cool stuff here that a lot of people have spent a lot of time working on. And some of them are really quite beautiful. Like, anyway, too much stuff all at once. So recurrent neural networks are good for sequences. There's also some really cool stuff too. And this is a really, really cool demo called Sketch RNN. And it's a recurrent neural network that was trained to draw simple, well, not, it's a recurrent neural network that was trained to draw with you. And it was trained on a very large database of people drawing like simple things, like draw a sailboat, draw like a sunny day. And you can start drawing, and the drawing is the sequence, and the RNN will attempt to auto-complete your sequence. It's really cool. And we also have some resources that show you how to use RNNs for something like time series forecasting. So we have a cool example on the website where you can predict the weather, like, what's the weather going to be tomorrow based on the weather last week, or something like that. There's another really important family. Let me go a little faster here. There's another really important family of neural networks called encoder-decoders. And these can be used for things like machine translation, and they're amazing. The basic idea here is that maybe you'd like to translate from a sentence in English to a sentence in Spanish. And you can use an encoder, which could be maybe an RNN, and that can read the sentence in English and transform it into a vector. And you can have a second RNN, which takes that vector as input and transforms it into an output sentence in Spanish. And so the encoder comes up with a representation for the data, and the decoder goes from that representation to a target language. I guess there's a lot here. I guess the main takeaway point is that prior to neural networks, you would do, when you wanted to do machine translation, you would have a team of like, programmers and statisticians and linguists, and you would have these really complicated systems that had lots of components and lots of rules, and they were very tricky to write and very complex. And when you switched to neural networks, you can go directly, like the only thing you need really is just a parallel corpora, which is sentences in English and sentences in Spanish. And the neural network can learn the machine translation process end to end. And so the code ends up being vastly simpler, and it's more effective too. I need to go a little faster here. There's a really important concept called attention that's become very popular in the last like 5 years or so. And basically, attention means that when you're doing something like machine translation, it enables the network to focus on different parts of the sentence. And you can also use attention in something like image classification. So if you're trying to decide if you're looking at a cat or a dog here, you can let the neural network zoom in on part of the image that's most important. So you can come up with something like scores for each of the pixels that say like, how much should the network focus on this pixel when it's trying to determine if it's a cat or a dog. And here you can see this mask where the network is focusing on the face of the cat to do the classification. So attention is a big deal. What's cool is that neural networks, you can also work with mixed data. So there's really awesome things you can do with something like image captioning. So you can have an encoder, which is built from convolutional layers. And here, what we're looking at is we have some picture of a surfer riding a wave. And this is a cartoon diagram of a convolutional neural network. And what we're doing here is we're pairing it with an RNN. So the CNN will come up with a representation for the data, and the RNN will go from that representation to a sentence. And it's just a really cool thing you can do. A really important class of models, which I think you'll see in Gus's talk, are things like transformers. And these are layers that use attention to do sequence classification. And the takeaway is that, I guess in 1 minute, still moving at warp speed, here is an RNN on the right here. And the goal of an RNN is to generate a sentence that describes what's in this image. And the way it works is it takes a representation of the image and a start token, which basically says start generating, and maybe it generates one word at a time, A. And then based on the fact that it just generated A, it considers its state, and now it generates another word, wave. And then based on the fact that it generated wave and its state, it will generate and. And the problem is an RNN is basically a for loop, which means it's very, very slow and it's hard to parallelize. And instead, when you use RNNs for sequence classification, they're very effective, but they're very slow because of this for loop. And a transformer is something that uses things like attention to process sequences, but in parallel. And so you can think of them as, it's a model that does sequence classification, but far faster. And that's made transformers very effective. There's another important class of models which are really quite beautiful called Gans. And all of the models that we've looked at so far are doing things like classification. Gans can do something like generation. And this is really beautiful. Basically, on this example here, we have these block diagrams of input images. And they correspond to pictures of like buildings and hotels and storefronts and things like that. And the GAN will start with a block diagram and attempt to generate an image that corresponds to the blocks. And so on the right here, you can look at the synthesized image from the GAN. And the way these GANs work is, there's two types of neural networks, and they're trained. So the reason they're called generative adversarial networks is the neural networks are trained adversarially. So you have one model, which is a generator, and the generator's job is to generate an image. And you have a second model called a discriminator or a detective. And the detective's job is to say whether that image is real or fake. And you train these networks against each other. So over time, the generator gets better at generating images, and the discriminator gets better at telling real images apart from fake images. And at the end, you have a model that can generate real looking images. And it's really, really cool. There's yet another class of models called GNNs, or graph neural networks. By the way, this was also work, surprise, out of MIT. And I believe MIT and Harvard. And you're trying to predict whether or not this molecule has antibacterial properties. And I have no background in chemistry at all, but I understand that you can represent molecules as a graph. Maybe you can do something like the atoms are nodes and the bonds are edges. And graph neural networks take graphs as input and can classify them. So I really, really like this paper. This is a very new area, but graph neural networks are also a thing. Just roughly, I guess one question that comes up is, why is deep learning so popular today? And there were roughly three things, or why did neural networks succeed? The first thing, which I don't have a slide for, is technological, is like basically on the computer science side, there was a lot of work into understanding just gradient descent and how is it that we can design models that we can train effectively with gradient descent, even if they're very large. And that's things like using ReLU instead of sigmoid. It's things like batch normalization. It's things like residual connections. So it's like the technical side of writing neural networks such that they can be trained. On top of that, we have very, very large data sets. A good example of this was ImageNet out of Fei-Fei Li's group from Stanford. So we have large data sets, and we also have things like compute, and that can be fast GPUs or other accelerators that you can use to train models at scale. I have like 3 more slides, and I'm just going to stop so we can take some questions. This is a lot of content. A common question that comes up a lot is, are neural networks opaque? And what that means is if you train a model to classify data, a really important thing, especially in something like medicine, is can you explain why the network classifies data the way it does? Like, can you interpret what it's doing? And the answer is sort of. There's different things you can do. A really amazing piece of work was Deep Dream. And Deep Dream was one of the first pieces of work that helped us understand exactly what a layer is learning to detect, or exactly what a neuron is learning to detect. And basically, let me see if I can, the way, this is going to be too fast, but basically, typically, when you train a neural network, you wiggle the weights of the network such that the network becomes more accurate at classifying data. After you've already trained a network, what you can do is you can wiggle the input such that some neuron gets more and more activated. So basically, if you're interested in like neuron number 5 and layer number 1 or whatever, what you can do is you can find an input image that makes that neuron as strongly activated as possible. And here what we're doing is we're starting with some static, and we're optimizing the static to activate some neuron in the network. And activate just means make its output as large as possible. And what we found is that some neuron is really excited by images that look like bananas. So there's literally like a banana neuron inside this large neural network that was trained to classify images. And you can also find an input image that excites an entire layer at a time. And so there's a layer in the network that is really good at recognizing faces. And we found an input image to excite it. There's other types of things you can do too. And I know this picture is small. So this is a piece of work called integrated gradients. And there's many examples in this family. Basically, if you have really good eyesight, which I do not, the image on the top right here is a fireboat spraying water in the San Francisco Bay. And we have some image classifier that said it's a fireboat. And now we're asking, why is it a fireboat? And this is a technique that's coming up with this purple mask that's highlighting the water spouts. And so we can say, oh, the neural network thinks it's a fireboat because of the water spouts. So there's different techniques in these families of neural networks. Another question that comes up a lot is, what is a neural network library? And there's a lot of good ones. So out of Google, there's TensorFlow, which is what I work on, and part of TensorFlow is Keras. And Keras is definitely what I'd recommend you start with. It's a really wonderful high-level library that helps you design neural networks effectively. And it has lots of great building blocks for different types of layers and stuff like that. But what a neural network library is, it's low-level code that you'll see from Wolf, which looks a lot like NumPy. And this is code to basically multiply matrices. It's like the fundamental building blocks that you need. Typically, you have something like support for GPUs, so you can multiply these matrices quickly. You'll have support for autodiff, which is used in gradient descent, so you can train the networks. You'll usually have building blocks like Keras, like things like layers, so you can write your neural networks quickly and effectively. And then you'll have an ecosystem of tools. And what's cool about TensorFlow, it's a huge framework. And it includes software that lets you write neural networks in JavaScript, or neural networks that run on phones, or I don't have one with me, but neural networks that run on little microcontrollers like a Arduino. And we also have lots of software for enterprise settings and stuff like that. So it's really huge. And the very last thing, I just want to show you one slide, then I have 2 book recommendations, and then we'll stop. So when you're doing regular programming, when your code compiles, typically, it might not work quite how you want, but at least it works. In neural networks, you can train a model that looks really accurate, but often it can be doing something that's not at all what you expect. And so this is something I borrowed from a class, but basically the idea is we have a neural network, and it's classifying this image as a horse. The issue is that when we apply techniques like integrated gradients to explain what is the network looking at when it says it's a horse, it turns out the network is looking at this tiny chunk of image on the ground, which has nothing to do with the horse at all. And so the network was learning to focus on something that was noise instead of focusing on the horse. So you had to very carefully evaluate your models. Okay, basically 2 book recommendations, and then happy to take Q&A. By far the best book that exists on practical deep learning today is called Deep Learning with Python. It's by Francois Chollet, and it's very, very important if you read this to get the 2nd edition. So the 2nd edition was published, I think, just like 2 months ago. It uses the latest version of TensorFlow, and it's phenomenal. There's basically no math, but it's an extremely practical introduction that will walk you through neural network fundamentals all the way up to complicated models like transformers. If you want academic background, there's a free textbook called Deep Learning. And Deep Learning is good supplementary material to Deep Learning with Python. But anyway, I can't recommend it highly enough. Students love it. It's great. So yeah, that was like a lightning overview of different chunks of deep learning. And yeah, I would recommend picking up the books, and you can use those to dive deeper. And then you can find on tensorflow.org/tutorials, you can find tons of practical code examples that will let you, try the techniques in practice. And all of the code examples on tensorflow.org, they are Jupyter notebooks, so you can just download them or run them on your own machine if you like, and you can directly open them up in Google Colab. And a good place to start if you're brand new to all of this, what I would recommend doing is just going to Machine Learning Basics and just start with basic image classification. And this is a nice tutorial that will walk you through classifying really small grayscale images of clothing. And if anyone likes, I'd be happy to walk you through exactly how this works. But that's a lot of talking, so I think I'll stop. Here, and happy to take any questions. So Lily has a good question, and I'd be happy to show you that with actually with this tutorial. So the question is, can you talk about your process of writing a neural network? For example, how do you go about choosing layers, and what do experts know that beginners don't? So that's a great question, and let's take a look with this tutorial. So what I'll do is I'll open this up in Colab, and let me see if I can make this change the background to white so it's easier for you all to see. And we don't need it for this, but I'm going to activate a GPU just so you can see how that's done. So let's get a GPU on. In Colab, the first thing I'll do is click connect. And again, this is a Jupyter notebook, you can run it on your own machine, but we'll just use Colab to make it easier. If I hover over this, you see that we have some virtual machine on Google Cloud with a GPU attached to it. And let me walk you through this, and then I'll explain the process of designing a neural network. So TensorFlow is a Python library, so we're importing TensorFlow. Deep learning always starts with data. I'm gonna, you can read the details here, so I'll fly through this a little bit. But we're importing the data set, and it's split into train and test. So we have images and labels. And there's a lot of code here. A really important skill in deep learning is basically poking around with the data to understand the shape. So here we have 60,000 images, each of which is 28 by 28. We have 60,000 labels, and the labels are between 0 and 9, which corresponds to the type of image, and so on and so forth. There's some code here to pre-process the data, and we're normalizing it. We're displaying the data. A really important skill in deep learning, which sounds silly, is just looking at your data and understanding exactly what's in your data set very carefully. Okay. So now it's time to actually define the neural network. And typically, the process here, this is a neural network with 2 layers. And a good place to begin would be beginning with the simplest possible model. And so here, we'll just use a single dense layer, which is basically logistic regression. And what you can do, or what I would do, is start with a very simple model and basically train the model and see how accurate it is. And so as we're training this model, it's trained sequentially, not sequentially, it's running through basically, we're training for 10 epochs. And an epoch basically means that it's used every image from the data set once, and it's classified it, and it's tweaking the weights of the network. And over time, as we train the model, it will become more and more accurate to a point. And after the model's trained, which should just finish in a second, we can evaluate how accurate it is. And this model, it looks like it's going to get up to like maybe 86% accurate. And then in the processes, you could start with a very simple model like that, just to get a baseline score. And after this, you could play with it and test it and see how well it works. And then you could gradually start making your model more complex. So you could add more layers, right? So if we wanted to do, now we have a neural network, now we have a deep neural network, now we have a deeper neural network. And we can increase the width of each layer to make the model more powerful. And with a more powerful model like this, it will probably overfit on the data. So it will memorize the data set. And then what we can do is so this model will probably be like 99% accurate, but it will have poor test accuracy. And then eventually over time, we can try and find a model that's maybe somewhere in between that will have good accuracy on train and test. So basically, you can experiment with different types of models. You can experiment with different types of hyperparameters. What experts would do is, I think the main thing is they would have just a larger awareness of the different types of models that are available. So, from Gus's talk, for example, there are models that you can reuse for image classification instead of writing your own. So designing neural networks themselves is a little bit like, it's a bit of an art. The issue is there's all of these parameters that we can adjust. We can adjust them by hand. Something that experts will do is hyperparameter tuning. So if you look for, there's a nice piece of software called Keras Tuner. And this is a hyperparameter tuner that basically, instead of manually adjusting all of these parameters by hand, you can give it a range and it will automatically try and adjust them for you. So there's stuff like that. That was a bit of a rambling answer. It's early for engineering hours, but that's okay. What other questions can I take for you? I'm going to find this book for you. Huh. Very strange. Anyway, when their website is fixed, here's a link to the book. Thanks, Leandro. Oops. I think I was accidentally sending direct messages, so let me rephrase that. There we go. So where do you see machine learning research headed, and what are some open problems being investigated? So I am super, super excited by GNNs and application of machine learning to drug design. And I know it's one of the reasons I guess I'm excited about it is, it's something totally out of my field, but I see a lot of like really cool humanitarian impact. And I suspect, I think, and I really hope it's going to be huge. I would love to see these neural networks be used to design drugs that, maybe 15 years down the road, it'd be so cool if, we had like a better version of Advil that, was designed by or partially designed by a neural network. There was really cool work out of DeepMind, I think earlier this week, using neural networks for programming competitions. And I think they did better than they did in the past. So that was a piece of work using these large language models to generate code, which is really cool too. That's helpful to people like me, because if we're writing code all day and we have assistive tooling that can help us like auto-complete our code in a smarter way, that can be very helpful too. And then I think another thing that's really cool is applications of deep learning to new domains. Like, for example, I know very little about business. I know very little about like mechanical engineering. And so when you have these combinations of domain experts like yourself, plus people who know deep learning, you usually can find new applications that are pretty cool. So a good strategy is basically just doing interdisciplinary stuff and like partnering with people in different departments and finding new applications. And those don't have to use really fancy models. They can just apply the existing technology to a new problem that just hasn't previously been explored. So there's a good question. What types of deep learning or even types of layers that are currently the best at 3D images? And so there are 3D convolutional layers. So Keras has convolution 3D, and which you can apply to 3D things like CT scans. By the way, we have tensorflow.org/tutorials. And Keras has its own website. All this runs on TensorFlow with a bunch of really cool code examples. And I suspect, almost certainly, there's a 3D, yep. So 3D image classification from CT scans. So check this out. And of course, when you're doing this stuff in 3D, it's going to be pretty slow because that's a lot of data. But this will show you how to use 3D convolution to process these volumes of image. Yeah. And I think if you look at the dimensions of this image, just guessing, this is most likely saying that the image is 128 by 128 pixels by 64. So I think we have a stack of 64 of these things, and then it's grayscale. But I could be wrong. Please go through this yourself. What's the difference between Keras and TensorFlow? That's a good question, and it's a little confusing. Keras is a neural networks API that runs on top of TensorFlow. So TensorFlow provides a lot of the low-level like compute and the low-level code you need to do backpropagation and gradient descent and things like that. And Keras provides these really nice layers, like things like, like this is what Keras is providing, these really nice neural networks like layers that make it easy for you to define models. They used to be separate libraries and they merged a few years back. So Keras is now part of TensorFlow and it's awesome. Yeah, so TensorFlow has been around for a few years. It was already great back in 2017. What new features have you and the team been working on? And where do you see TF going moving forward? Yeah, so we're always making TensorFlow easier to use. There is so much happening in TensorFlow so fast that I think the best way to answer that question is I'm going to give you a link to the blog. And you can see, basically, this is just new things that have been happening recently. So I mentioned that I'm really excited by graph neural networks. TensorFlow now has a graph neural networks library, and the team is working really hard on additional features for this. But this is something that you could use for the things like antibiotic discovery. So those are new types of layers for graphs. There's a lot of really cool work going on in JavaScript. And so basically, these are these really high performance models that you can use out of the box to do like motion detection and things like that. So applications built on top of that. There's a lot of work being done on TensorFlow Lite just to make these models run more effectively and easier to use on Android and iOS. Let's see. There's new work being done basically to make TensorFlow easier to use. So one thing that's traditionally been hard is just writing the code to pre-process your data sets and feed them into the model. And so we've been working on code in Keras just to make it easier to process images and text and things like that. There's been a lot of community work. Let's see. Anyway, there's just a lot of going on, and we've been doing lots of partnership work too. So we're working with lots of just different companies around the world just to make sure that TensorFlow runs really well on their hardware. So yeah, it's just a lot. But yeah, it's yeah. So basically, yeah, you can poke around and find things that are interesting. And then what if you have the coordinates for the 3D object rather than a CT scan? So I think what you might be asking about, although I'm not totally sure, is I'm not an expert in this area at all with 3D stuff. But another thing you can do instead of image classification is you can do image segmentation. And so here we have a picture of a cat, and in image segmentation, we're trying to find a bounding box around the cat. And this can be done in 3D, although I've never done that myself. So I'll give you a link to the image segmentation tutorial in case that's helpful. And then a good strategy too is in deep learning, this is sort of a large repo of many different things you can do. And cool, we even have graph neural networks here now too. And one thing you can do is find the problem that's similar to something that you're interested in, and then go from there, like modify and go from there. And then another good question, are there machine learning papers with no math? Yes, many. There's always a little bit of math, but mostly in the evaluation. So one of my favorite papers was also the work, her name is also Lily. This paper, Accuracy of a Deep Learning Algorithm for Detection of Diabetic Retinopathy, did not have a ton of math. And the reason is that it was a computer vision paper, but it wasn't doing computer vision research. It was an application paper. And so the math was in, basically evaluation to make sure that just some statistics so they could see how well the models are working. But there shouldn't be any like calculus, and there shouldn't be any linear algebra in there or anything like that. So how can we find more papers like this? That's a good question. I guess it depends on the field. So these are application papers. So I would look for a field of interest to you. I would look for, you can go on, I would search around for like deep learning plus that field. One thing to be aware of too, there's so many papers and it can be hard to find good ones. So, you could look at like citation counts. You could ask different researchers in the field or different practitioners. But yeah, What other questions? And if we don't have any, we can stop early too, and you can have a break before the next session.
I think that's like a whole lot of questions here, and it's really nice to see people like asking questions around that. I have a quick question actually, Josh. So how do you actually think about the math when you are like looking at the layers, and how do you like keep an eye on both the math and the layers when you are thinking about different problems, let's say image classification, graphs, and all around it?
Yeah, that's a really good question. And so it depends. So to what extent do you need to think about the math when you're building models? And the answer is it depends on what you're doing. So usually in practice, I don't at all. Because the layers, I understand what the layers are doing. So like as you learn this stuff, again, it takes about a semester, at least. When you learn this stuff, typically in an academic class, like if you take a class at MIT, that class will cover the math inside this dense layer. So you understand exactly what it's doing. But in practice, when you apply it, I don't need to know the details of the matrix multiplication. I need to know what the layer is trying to do at a high level. And if that helps with your question. So it's basically, you can think of, you have a box of layers that are suited for processing different types of data. And when you learn this stuff in practice, you begin to learn different combinations of layers that work well for different problems. And so when you're designing networks, it's more of an art than a science. Where the math does come up is typically knowing the size of these models. So for example, one thing you often want to know is how many parameters are in your model. So basically, let's see if I'm still connected. Yeah. So I did a summary. This is the model we use to classify these MNISTs, these little pieces of clothing. Model.summary can tell us how many weights there are in the network. And here the math is helpful because basically, just in the sense that smaller networks are more efficient and train faster. And also maybe someday you want to save your model and run it on a phone or run it in a browser. And so having a sense of how heavy these different layers are can be very helpful. But again, that's in practice, that's high level. I'm not thinking about the details of the matrix multiplications. Where you would need to know the math is if you're doing computer vision research and you want to design a new type of layer, like the MIT convolutional layer, then knowing the details there would be super important.
Okay, there's a question from Corey. I have a super quick question there. When you say about like just thinking about like what layers would apply in a specific field, let's say vision, like transformers, I understand like BERT was designed for language models. And suddenly we see that everybody has been like flattening their images and doing VITs or vision transformers. Like, is it that we throw everything that we have on the wall and see like what sticks? Or how does this intuition come up? Like I'm trying to differentiate the art from the science and try to see like what's the difference there.
Yeah, to be honest, it's mostly art. So it's like,
okay, that answers that very quickly.
typically, so what I think what's happened in deep learning is that the science has followed the art. So basically, a good example of this is Deep Dream. So we had really effective image classifiers for a long time. And then it was only a few years later that it was like, now we have a sense why they're working. And I think with transformers, yeah, it's the same. Yeah.
Fair.
Yeah.
That's a question in the chat. Yeah, actually too.
Okay, so two questions. So one, can you talk about the typical deployment of deep learning in a business setting? And I've used Colab before for education, but not sure what the actual implementation would look like. Yeah, that's a really good question. So for any kind of model, and it doesn't matter if you train in Colab or somewhere else, basically you can do model.save. And that will give you a binary that you can later serve. And there's different ways to serve it. There are managed cloud services. So I don't use Google Cloud. I don't work on Google Cloud myself. But if you search for Google Cloud TensorFlow Serve, there's a managed service where you can deploy your model, and that's probably what you want. But you can also serve your models in open source using something like TensorFlow Serving. And so we have packages you can download that will let you spin up a server to serve your models. So typically something like that, and you would surround them with maybe like a REST API. There's other ways you can deploy models too, depending on your business setting. We have something called TensorFlow JS. So you could even deploy your models in a web page via JavaScript. But that's a good question. And then the next question is, so I would start by, depending on what you're doing, you probably want a managed cloud services. So I shy away from cloud services for educational settings. But once you move into business and you actually are building something that's going to have revenue, it's almost always worth your time to use the cloud, because the engineering effort that goes into rolling your own infrastructure is probably better spent solving the machine learning problem that you want to solve and just pay for the serving, just so you don't have to worry about that chunk. It will save you a lot of time. And then another question, so how do you think about updating or retraining models? And you had a model in the wild, how do you know when the weight should be updated? So that's an excellent, excellent question. And it's very, very important. And the answer is, it depends. It's when the distribution of your data might have changed. So for example, a classic example of this would be recommendations. And let's say you build a recommendation engine for like the month of February. Maybe it rains and it snows a lot in February. So if you have a store, you're recommending raincoats and you're recommending umbrellas. But maybe in April, it's warmer and it doesn't rain as much. And if you run the model that you trained in February and April, your users are going to be unhappy because it's recommending things that are no longer relevant. So you would have to retrain your model based on the new data that you're making predictions on. And that's true in all domains. So basically it's whenever the distribution of the data changes, that's when you need to retrain your models. And in practice, for like enormous companies and things like, maybe Amazon retrains their recommendation models, I have no idea, maybe even once a day. So that frequently. And for a smaller company, it could be once a month or once a week. But it depends on the setting that you're making predictions. And to be honest, like the answer to that question is much more important to get right than, that will have far more impact on the success of your deep learning work than messing around with, should I add another dense layer? So once you have when we retrain answered properly, then you can really design your model. And the reason is like adding one more dense layer, getting your model exactly right might give you like 1% more accuracy or 2% more accuracy. But getting the when do we retrain it right is basically success or failure at all. So it's like that's why that question is so important. Okay, let's see. Are there ways to instrument the change in an input data distribution? Yes, we have tools for that. And it's funny, you got me. This is it's very rare that I can't think of the name of something, but I haven't given a talk in about 6 months because we've been just with the pandemic and stuff like that. I think a good place to start the pair team has tons and tons and tons of really helpful tools. And I would start poking around here. Yeah, okay, thank you. My brain is now working again. So if you're working with, so they have like really cool interactive tools to visualize images and text, different distributions of data. There should be all sorts of stuff here, and it'd be a good place to start. They even have stuff for health records. And then let's see. Worth noting that for some businesses, for data privacy, and data prefer to keep the development on-premises. Yes, absolutely. Yep, and cloud can absolutely become expensive in the long run, for sure. And so those are very, very good points. And for on-premise stuff, this can all be done on-prem. And yeah, absolutely. TensorFlow also has something called TFX. And TFX, it's basically designed for enterprises. So it's a ton of infrastructure you need to train and serve models at scale. And this is actually part of TensorFlow serving is part of TFX.
All righty. I think we are just 5 minutes short of 5 minutes to go for Gus's session now. Thanks, Josh. Thanks for giving this wonderful session with all the links and with all the help and giving an overview of entire deep learning architectures and all sorts of different models, data sets, and how we can work with that from an educational setting. That was really helpful with all the free tools that Google is able to provide to students. We hope to see you on campus sometime soon.
I would love to. Yeah, absolutely. Hopefully in a few months, I would love to swing up and just meet all of you. And yeah, it'd be great. I would love to. So please count me in the future.
Sure. And yeah, a virtual round of applause for you. Thank you.
Thanks so much. Again. And thank you for organizing and having us. I really appreciate it. I will be on Zoom the whole time. I'm happy to answer more questions. I'm just gonna get some more coffee and then I'll come back for Gus's talk.
Awesome. So Gus, here you go. And the floor is yours from here.
Hi, everyone. Can you hear me? Fine?
Yep.
Perfect. Nice. Let me present my screen. Give me just 1 second.
Sure.
So what I'm going to try to do with you all today is, given the amazing presentation that Josh just gave, I'm going to follow up with how to implement some of that easily. I'll give you all the tools and links and resources. I'll have 2 exercises if you want to do yourself. So that's fine. I'll give the link, but I'm going to go over them during the code so you can understand what I'm doing. And then that might help you understand better. I saw many questions that you might get some more clarity when doing these collabs, these exercises. And I hope it helps, of course. That's my goal. And the other thing is I might not pay too much attention to the chat in terms of questions because so I don't mess up anything, but I'll do a first presentation and then I'll go to a first collab. And then if you have any questions, please feel free to ask them every time I give a pause, because then it's a little bit easier for me. So let's go. Can I start? I guess I can, right? We're 2 minutes early, but that's okay. First of all, good morning for everyone. I'm Gus. I work on the same team as Josh. You can find me on Twitter at Gustema. I usually talk about machine learning Python every day. So that's a good opportunity to keep up with content. And today I'm going to talk to you about TensorFlow Hub and how to have access to all these state-of-the-art models that Josh just mentioned, and how to use them on your work, even if you're not like a researcher, an expert, if you're just like a developer. I'm a developer, right? So if you're on that stage, you can use these models. So as developers, we try to reuse code, right? So if you know how, for example, sorting a collection, it's very rare where you go there and you implement a quick sort or any sort method by hand. That's not something you do on a regular basis. Usually you use something like you use the proper sort method from your language of choice, right? So we try to reuse code, reuse components that were created by other people. And in machine learning world, we do the same thing, right? We don't always create models from scratch. We sometimes use the work of some other people, some other researchers. So for many tasks, to be sincere, you don't really go and create the model, even if you want, because that's a lot of work. You try to reuse these models from other people. So for example, for object detection, understanding how what is object detection? Given an image, you tell where a dog, for example, is, but not only, oh, there is a dog. It's more than that. You show where the dog is, right? So it's more complex than just telling, oh, there's a dog there. So doing this kind of model is complex. It's not something you are going to do it like in a week from scratch, right? It takes a lot of work. The same for audio classification. How do you do audio classification? That's tricky. There's a lot of details to go from the raw audio to a proper classification, and even more complex when you start talking about text, right? Text is absurdly important and at the same time very hard for machines to understand. And how do you go and solve these problems and in a way that's available to everyone? And that's the point. The other important thing that you have to take in mind is if you want to build a machine learning model from scratch, it takes a lot of resources, and one of them is time. Sometimes researchers take like a month training a model, right? It's not for everyone. Not everyone can just, I'll spend this month training one model or 2 experiments or something like that. So it can be very tricky. And if you're training a model from scratch, you need a lot of data. You cannot just, let me take some pictures here and train my own model from scratch. That's not how it works. You need a lot of data. And more than that, you need a lot of expertise. So I saw many questions about which layers would you use, how the math connects. And as Josh said, there's a lot of art and there is a lot of knowledge about the data, knowledge about the problem that has to come with it. And this is not something that you might not have available, right, for all the time. And of course, to train a model, you also need a lot of resources, a lot of computer power to train a model for a week. Some models are training for a complete week, full time on machines, and to get some result that sometimes it's just, not good enough. Let's test another parameter, try again another week. So this takes a lot of computer power. And as I said, it's not available to everyone. So this would be very limiting. And that's something that we're trying to solve with TensorFlow Hub. TensorFlow Hub is a repository of pre-trained models for you to freely use any way you want, right? You have access to not only the model, but documentation, sample code, an explanation of when to use that model, when not to use that model, license, everything is connected. And it's particularly simple to use, and we are going to see how to use it. In a sense, TensorFlow Hub has 2 components. It has a website, which is tensorflowhub.dev, where you can search for models, read the documentation, read this sample code and all those kinds of things, and where you can find models for all kinds of tasks. For example, image, you can find models for all kinds of image tasks, for example, classification, object detection, style transfer, super resolution, all of those. Not only for image, we also have models for text. And if we have enough time, I'm going to go specifically over text and explain some more details about it. There are some specific aspects of text that I would like to share with you. Hope we have enough time. We also have models for audio and for video, which are usually you say, models for imaging, models for text, but we also have for audio, which has a completely different aspect of where to use. For example, if you want to analyze what's happening inside a forest, if there are chainsaws or if there are poaching happening inside a forest, you cannot use image, right? That cameras cannot target in the middle of the forest, but if you listen to a chainsaw, you can can act on it, right? So this is a different aspect. Or if you want to work with, I don't know, whales and understand their behavior, where they are, audio is better than image also. So there are many cases where audio can give you a perspective that images cannot, right? And in the fun part is that solving audio problems, it's very similar to solving image problems, right? But I'm not going to go into much details on that. Also, we can do video. Video is more than a combination of many images in a row, right? Because it's not like one image impacts the following, right? They have a sequence. So video is a combination of image classification plus series analysis, right? Because there is a sequence of stuff happening, and which is important, right, to understand video. The models we have on Hub are also they have other perspective. They are not only for you to do research or stuff like that, but you can deploy them on production. So when I talk about TensorFlow Extended here, which Josh also mentioned, TFX, is when you need a model to be part of your model or just to deploy directly on your business environment to do some, I don't know, image classification. Let's go with that. You can do that. You can also deploy some of the models are converted to be deployed on a browser with TensorFlow JS. So, for example, I don't know if Zoom has that. I don't use Zoom that much. I use Google Meet, as you would expect, right? And there is a feature that I can blur my background or change my background to be in a theme park or those kind of fun stuff, right? What's happening there is that there is a model doing image segmentation and finding a person, and then it takes everything that's not a person and put another image there. That's a model that's running in the browser, right? It doesn't go, usually it doesn't go to a server and then do all the process and come back. That would be too slow. That's running on the browser. You can also run models on mobile devices like a phone or a Raspberry Pi or a Coral device. We also have models on Hub to do that directly. Models to run on browser or a mobile device, they need to be converted, right? They're not exactly the same model. And this conversion is needed because some models are just too big, too complex, and you cannot run that on a mobile device, right? So when we convert, we make them smaller, faster, with some, maybe we lose some accuracy here and there, but it's still very close, but smaller enough to run on a device. So for example, if you are taking pictures on your phone today, I'm pretty sure that every modern phone is applying machine learning to whatever picture you're taking, right? Even if it's a filter, making it better, denoising. For example, when there's a blurred face, they try to fix that. All of that is machine learning running on your device. And we have many of those models on TensorFlow Hub for you to use directly. We have thousands and thousands of models for you to try. And of course, they are not thousands of models that are completely different. There are many models that are for different image resolutions, the same model image, different image resolutions, or for example, models for text, but for different languages, which also can make a difference. So we have all these models. We are going to go in details in a little bit. Also, beyond having the models, the documentation, sample code, some of them, they have like a widget on the documentation page that you can try the model right there. For example, if there's a bird detection, that you can just drag an image and it will classify if there's a bird or not on that image. Easy as that. Same for plant diseases. There's for food. There's many of those that you can play with, and you don't even need to download anything. You open the browser, see the documentation, drag an image. If you see if the model works for you or not. That's a fun thing to do. Here we see a documentation page from a BERT model. BERT model is a language model, language-related model. And one important aspect of the documentation we have is that button you can see there, which is Open Collab Notebook. And what does that do is from this page, you can, I want to try this model in code. You can open there, you can click, it will open a collab for you with all the code you need to use that model, with explanation, with tips and everything you need. So you have a lot of resources to use many of those models. And that's what makes it more accessible to everyone. I said there was two components to TensorFlow Hub. The website that we saw, main aspects, I can go over in practice later. But we also have a library. And what this library does, it makes easy for you to give it a model that you found on the site, load and use that model directly in code, right? You don't need to download by hand. You don't need to click on the download button. You don't need to do any of that. You just need the model URL. So if you come back here, oh, sorry, I cut the URL. But on the browser, every time you access a model, you can see the URL. That's what we call the model handle. If you have that, you can load that model with like one line of code, load that and use that model already. We are going to see that in a little bit. Really, it's really neat. And we can also use those models to do transfer learning or fine tuning. And as Josh said, you can reuse a model that someone trained and get better results with that. We also take a look on that. What's happening behind? So here's a code sample for us. I import TensorFlow Hub as Hub. That's very typical. And then what we do is hub.load. Hub.load is the method that will get a model handle, as you can see there, and it will download, put on a temporary directory, and load that as a TensorFlow model ready to be used. So the embed variable there is a model, it's a TensorFlow model that's ready to be used directly. And then I just do embed in some inputs and I'll get the results. This is how you use a model from TensorFlow Hub. Quite easy, right? Behind the curtains, what's really happening is Hub is going to our server and then it finds the asset, downloads locally, creates a cache. It comes compressed, of course. It decompress, puts in a temp directory that you can change if you want, and just loads it to memory. We do all of that because if you need to, you can take a look on the model if you want, but if you call the same cell again, the same code, it will try to go to the cache first before downloading anything. So if this is part of your pipeline somewhere, you're not going to keep hitting our servers, not going to use bandwidth on your cloud server if that's a problem for you. And the model will be there cached to be loaded faster the next time. Sometimes you also need to access the model directly for, I don't know if you want to look into some specific file like a configuration or some dictionary or something that's that came with the model, or if you want to convert that to TensorFlow JS or TensorFlow Lite. So there's some use case where you would like to see the model, but that's, let's say that's not something you do very frequently, right? Okay, I told you a lot of stuff, and let's see some code, right? Let's take a look on some code. So if you follow to this URL here, let's see if I can, oops, sorry. Let me just do this. I'll put on the chat. Sorry. So if you want to follow me on this URL, you are going to land on, oops, this collab here. So what I'm going to do with you, I'm going to go over this collab line by line so you understand what's going on. And you understand, I don't know if you ever used Colab, I can give you an introduction to that. So what is Colab? Colab is a hosted notebook, Jupyter notebook environment. It's hosted on a public VMs that Google provides you. These VMs have access to GPU, sometimes to TPU. If you want to do more, if you need more resources, they're completely free. There you can subscribe to a pro version which has some advantages. But for if you want to, if you're just learning machine learning, this is a perfect environment. And I use that every day. That's my main environment, Colab. I don't even try stuff on my machine. I don't want to deal with environment, to deal with libraries that I don't know how to install locally. Sometimes you need to do some crazy stuff to install proper libraries. On Colab, everything is installed. If I need to install something there, I'll do it. And that's fine, and everything works. So I highly suggest you put that in your belt of tools, right? How, let's see what we do here. So this collab, we are going to do just image classification, right? Nothing else, just image classification. So there's a question since I just saw, is it difficult to run batch jobs, multiple jobs on Colab? So there is, the batch word is a little bit overloaded. So we can have like for free, I guess 2 or 3 collabs running at the same time, right? If you want to do many collabs at the same time, then maybe collab won't be the same thing for you. But I guess for my experience, 2 or 3, I don't know how many is the limit, maybe 2 is enough because I'm paying attention to the same execution for one time. But if you need many at the same time, running lots of experiments at the same time, then you need your proper VM on your cloud provider or even on premise, right? If you have proper machines for that. So that might be a trick thing, but when you're learning or for testing stuff, it's perfectly fine. Let's start by running the first cell here. So let's do some image classification with TensorFlow Hub. First cell, what it's doing is, of course, importing the libraries I need. And before we do that, I forgot to see something. So if you come to change runtime, you can see here that I'm already using GPU, right? So I'm connected to a machine and I have access to GPU, right? Why that's important? Every time you're trying to train a model or to run stuff on run model related stuff, having access to a GPU is a good thing because it can change from 10 minutes executing a cell to like 10 seconds, right? Because GPU gives you so much more power in terms of processing. So it's always good to take a look if you have access to a GPU whenever you're running something. Why I'm doing that right at the start, because if I change here to something else, or TPU or non, which would be CPU only, it will restart my environment. So if I run like 10 cells and I change the runtime, it will restart everything. I'll lose all my work. So it's always good to look into that right from the beginning. A little bit more about Colab. What I like most about using this kind of environment is, you see this, right? This is the documentation that you can write. You can leave all kinds of proper documentation of what you're doing with links to a paper, links to other notebooks, doesn't matter. You can document everything using markup language. And that makes life, you can share this like any Google Docs, like a docs, a sheets, or a presentation, you can share with your friends. And that makes a huge difference to have a good documentation so that everyone can understand what you're trying to do, right? So this is a good aspect of having this kind of thing. I also execute these helper functions here. They're hidden because they're just kind of boilerplate code to download images. I'm not going to go into details here. This is basically downloading an image, right? It's not something related to machine learning at all. And now we are doing something very interesting here. So as you can see here, I have a combo box here where I can choose a model, right? I can choose among many models. Let's start with this EfficientNet V2 small. And what does it mean is, for any model I choose here, it will get a model from Tensor. You can see all these URLs from TensorFlow Hub here, right? It will choose a TensorFlow Hub model, which is here, model handle. Different models, image models, they have some different input size. So there are models that will take images that are 224 by 224. Other models are 512 by 512. So the input size of the model is different. Of course, models that takes bigger images as input, the model by itself is bigger also, right? So it uses more resources, need more power to run. So this is why this is important, because if you are just trying some new ideas, you can use a small model just to play. Or if you are deploying on a mobile device, you should use maybe a small model also, because small devices cannot run inference on super large images. So this is an important aspect. You can see all of this in the documentation, right? The image input size, it's in the documentation. You can just do that. We chose this model here, EfficientNet V2, right? So when I run that, I came to this model here, right? And if I follow this link here, this is the model we are going to use, ImageNet V2. It's for classification. It's just the model URL. That's the URL I used before to load the model. As you can see, there's a Colab. I can download the model directly if I want. I have some ideas of how good this model is. So we are talking about V2S might be around here, right? So we can see there's all of this documentation for me to read and pay attention and see if that's what I want or not. We're using this one here, right? Yes, V2. Yes. Let me see if I'm using this. Yeah, that's correct. On ImageNet 1K. Yes, this is one. So this is the model we are using. You can see here I have a way to use the model, some code sample. And if I want to fine tune, we're going to do this in a little bit. Don't worry. All this documentation, all available to you. Let's go back to our model. The model is already loaded in memory because I did load it. Where's here? Oh, sorry, I didn't load the model yet. No, I didn't. I selected, I'll load it in a cell below. And here we can choose a specific image. Let's use the leather turtle here. Let's download the image. We can show the code that's doing that. I'm not going to put too much time here because it's, again, a lot of URLs from Wikipedia. And then I just use the download image method we created earlier, right? Here's the image we're going to classify. And now it's where really code that you need to understand comes. First line here is hub.load and a model handle. Model handle is what we got here, which is that URL that I showed you in another page. And we also have shape. Remember I said the image input size That's important. And what we're going to do here, we're just loading a model and applying to random data just so we warm it up. Why do we warm it up? Since this is a sample collab, if you want to measure how fast a model is running, you have to remove the first execution, right? Because that's when you download the model and when you load it from memory. So it's not exactly how fast the model runs, right? So you can see that it took 10 seconds. It's not going to take 10 seconds per image, right? Otherwise it would be horrible. And here we're going to properly run the method. Here we have the classifier, right? Classifier is our model here. Here we have classifier, and we will give the image. And what it returns is not exactly I don't know what you expect from a model to return, but what this returns is the range of likelihood of the image being what you want. So I'm going to run this and I'm going to debug for you exactly what happened. So here you can see that for this image, there's a 77.77 likelihood that it's a turtle. So yeah, correct. Hooray, right? So that the model is correct. And that's class 35. What does all of this mean? This model was trained on ImageNet 1K, right? So ImageNet 1K has 1,000 labels, and label 35 is a leatherback turtle. That's why it's written here. What kind of results does this model returns? We can do exactly that for you to see. If I run the model, this is what it returns. It returns a very long array with 1,000 positions. And for each position, there's a float number. The higher the float number, the more likely of the class of that position being the correct one. Kind of. So my goal here is, given this 1,000 position, why 1,000? Because the model classifies 1,000 classes, right? So how do I find the highest number on that array? Using the Softmax function. It will give us, first it will compress into a distribution, and then after that I'm going to go and do the arg sort, with finding the argument that has the highest value here, right? Sorry for my mistake here. This is what I'm going to find the ID, that I find the top 5, but I can find the top 1 if I want. And then I will just find it here. So if it will be hard to find the 30, which is turtle? 35, right? If we find the 35 here, 35th item, it will be the highest value in this array. So this is how classification works. If you want to train with a change and try another model, you can just come here and try let's try a bigger one. Let's try this one, a large one. So what this does is it will load a larger model. I can, same image, I'm going to load it here. As you can see, it takes longer because it's a larger model. You see my screen? Yes, yes. As you can see, it's way longer, right? So let's take a look on this model here. So that other model, the small one, had 77 megabytes. This is 400 megabytes of size. So there's a big difference here, right? It's that's weird, but that's I'm trying a different thing. So let's try something different. I'm going to leave this here because I don't want to lose these values. We can just do this, and of course we have a better one. Oh, that's fun because look, the value here, it's smaller. So this model, even though it's bigger, it's not giving the best results for this turtle. Before we had 77, now it's 15, which is a little bit weird, but it's still correct, right? It's still correct. So this is how we run inference with any modules from Hub. That's very similar to running the same code here. Load the model, and then you just call classifier on an input here, and that's it. Basically, that's how you do inference. If you want to try something more advanced, we can try transfer learning, right? So if you have questions, that's a good time to ask your questions. And while you can ask your question, let's try some transfer learning with image also. This is a little bit more tricky. URL. And my transfer learning is here. Is this training set for a single model training?
Quick thing,
Yes.
sorry. Yeah, there's a couple of questions in the chat. We might, like before moving on to transfer learning, I think.
Of course.
Yeah.
Bring them on.
Sure. So one of the first one was by Lily. What is inside a model file? Is it the structure of the layer and some parameter numbers?
Yes. So what's the model is basically all the structure, like it's like a graph, right, of layers, and all the weights for each neuron, let's say like that. So remember the image that Josh showed that there was like a base input and a lot of circles that went to small circles. For each circle, there is a weight, a number associated with that. So a model is basically the structure of the model, like all the computation and all the weights for each parameter that you have. So this is basically what's inside a model, right? And that's what's saved locally, which can be loaded. So this, when we load a model, we are not loading like an image, you load data, right? When you load a model, we are loading a computational graph for execution. So it's more complex than just data, right? So that's what inside a model.
Thanks. There's another from Israel. Isn't it difficult to run batch jobs or multiple jobs on a collab?
Yes. So the idea is when you're doing collab, when you're using this environment, you have your own VM to run your code, but it's one code that's running, right? You cannot run many experiments in parallel. That's not something you'll be able to do here. You would need your own cluster of machines or your own local machine. You might be able to run multiple scripts. On Colab, you run one experiment. The problem with there's a problem with the word batch, because machine learning has the batch idea, where when you train a model on a data set, you divide this data set in batches, right? So this is another aspect. It's different understanding, but for machine learning, for batch training, that works fine. You can have like many batches, it will train one after the other. So Collabs works for that. But for I guess what he meant there is if I want to train run many training jobs at the same time, different training jobs at the same time. So for that, it would just one collab wouldn't be enough. You might need a proper on-premise or a cloud environment to do that.
Fair. Thank you. There's one last question from Josh.
Yes.
It's a pretty long question. So Josh, if you can unmute and ask that, that might be more helpful.
Yeah.
Okay. Yeah. Josh is unmuted, I believe. All right.
Hey,
yeah.
Can you guys hear me?
Yeah.
Yes.
Okay.
Yes.
Yeah.
Yeah. So the question is just, is it more efficient to use in the training set that we're using here to have it just immediately classify out of, all sorts of animals and various photographs, whether, exactly down to the subspecies of turtle as we were showing, or does it make more sense to kind of go multiple layers where you're classifying first, is it a turtle or not a turtle? And then if it is a turtle, then what kind of turtle is it?
Yeah, that's a very good question. The idea, what we did in the other collab here, is that the model that was used, it was trained to learn 1,000 classes. So in these 1,000 classes, I guess it has more than one type of turtle. It has also lion, tiger, elephant, piano, apple, banana, rose, ship, truck, car. So it's a lot of stuff in these 1,000 classes, and they're not all of them related, right? And it learns to look into an image and say, oh, there is a turtle. And also might there be a tiger? I don't know. So this is a different perspective of what you're trying to say, that the model should learn to, oh, this is a turtle. Which kind of turtle? This is different. It could be done, but that's not how these models are usually trained. They are trained on this ImageNet is like a very basic data set, not basic in terms of small, but because everyone uses it. Let's use it and see how our model behaves on this, because it's what everyone uses. And they're used to this 1,000 classes thing to be how it returns. So your idea is good, but given that you would need a data set that does all turtles, and then from there you find types of turtles. And then there's a thing that we can get from your question, which is, okay, I got this turtle here, but I work for Projeto Tamar. Projeto Tamar is a project in Brazil that they try to protect turtles from extinction, right? And for them, if they want a model that looks into an image with a turtle, they want to know which turtle is that, specifically, not only that one, but all of the other possible ones. How would they do that? Because this model, as it is not going to give them that information. If it's a turtle that's not in the data set that was used to train this model, label as a sea turtle, for example, it's not going to be able to tell you this is a sea turtle when a sea turtle shows up, right? Or any other kinds of turtles. So how do I address that? How do I fix that? That's when you would use, for example, transfer learning. What's transfer learning? Transfer learning is you have your own data set that is usually a subset of a big data set. So if I have a data set of turtles only turtles, and I have 100 pictures for this leather, sorry, I'm not an expert on turtles, leatherback turtle, I have 100 images for sea turtles, 100 images for another turtle, and I have images for all of them, and I want my model to now classify my turtles, all these, right? How do I do that? That's when you can use a model like these ones that I showed you and use their expertise to learn features in an image, which is basically what they did, right? Josh mentioned that. A model learns what's drawn, right, on an image. It learns what's like an ear, a nose, a curve, a sun. It learns all these basic things. And from composing all of them, it can tell you if there's a lion in the image, right? So it learns these features, these patterns. If I want to create my own model, my first step is let me get a model that knows a lot about images and make this specific for my data set. Making this specific for my data set is called transfer learning. That's the next thing we're going to see. That's when you can create that's where I would start for anyone that wants to create a machine learning model, right? After you know the basics and you have data set, usually you don't create from scratch. You get a model and you do transfer learn to your data. And then you have at least a baseline to try other thing, right? To try your own if you want. So this is the next step we're going to do. Does it make sense, Josh?
Yes, thank you.
Is it possible to build a neural network with intermediate or nested classes as the result? Memo. So there is. I'm pretty sure you can do that. The thing is, I never did it, but I guess you can do stuff like that. Yes, create a neural network that has memo, and then inside it classifies as horse or dog. Doesn't matter. So the thing is, if you have data for that, that's more hierarchical data, right? So you have layers of memo. Below memo, you have other stuff. Below turtle, you have leatherback, sea turtle, or whatever turtle. That's something that you would need a neural network that's hierarchical. Maybe a graph neural network could do that, right? Because they can model hierarchy of information. And that's something that maybe a graph neural network could do. I'm not an expert. I don't know if that's how things would work, but I'm pretty sure you can do exactly that. The only thing you need there is a data set with these kind of sub-labels per image, right? And I don't know if that's available, to be very sincere. Any other question, or I can continue with transfer learning?
Hi guys, I have a question on transfer learning. Can I just drop in here?
Of course.
Yeah, sure. You talked about like how transfer learning can be used in different areas. If I give you a scenario, like if I want to classify images in manufacturing, like detecting good quality parts and bad quality parts, is it okay if I use a pre-trained model, which was trained on like animals, birds, but now I want to use it in the manufacturing domain. So will it be helpful because these two domains are completely different? Will the model work better?
That's a very good question. So the question is from Satvik is, can I use any model to do transfer learning on my data set? Or should the pre-trained base model be related somehow to my data set? If you can find a pre-trained model, train on a big data set that the images are similar to what you're going to use, it's better. And we have we've tried that many times, right? But sometimes you don't have that. So for the factory thing, if you don't have that, if you try a very good generic model like mobile.mit, for example, which is a new one, very good, very high accuracy rate, that could give you absurdly good baseline, maybe 80% accuracy, which is very good, right? And if that's not enough for you, and you say, oh, no, I want to do better, and you don't have a pre-trained model with a proper data set similar to yours, at that point, you might have to go and train the model from scratch with your own data, right? And see if that will beat your baseline. Sometimes you won't be able to do that. There are many techniques to increase the amount of data you have available. Some image augmentation, which is more some other topics still on machine learning that can help you. But that's I guess for a start, I would take a model or maybe a couple of them, try to train them with my data set, get their results, and go from there. So the first step, trying transfer learning, might not be the best, as you mentioned, but you have a baseline, right? So you're not starting from zero. From there, you can evolve. And does it help to have a data set that was close to yours? Yes, but that's not always possible. Does it make sense?
Yeah, it does. Thank you. So it boils down to trying out different methods and choosing which one really works.
Yes. So we did a sample where we want to find bean plant disease, right? So we have a lot of images of beans disease, and we tried many base models to do transfer learning. Many of them have results like 50%, 60% accuracy, until we got one that was, the base model was trained on cassava leaves disease. That one gave us 90-something% accuracy just by changing the base model, right? We didn't change anything else. We changed the base model from Hub. So it's an experimentation step. And this gave us 90-something%. So the base model, of course, it was based on cassava, which is also plant related and disease. So that shows that a base model that has data sets similar to what you're trying to do, of course, helps you with understanding image better. Right?
Yeah, thank you guys. That really helps.
Of course. Let's start running this, and then it's very similar. Let's start from, of course, the initial setup. Here it's, so this collab is very similar to the other one, is more advanced, of course, but the idea is similar. We need some dependencies here, and oh, good, 2.7. Let's see if we are using. So for this one specifically, if you're following me on Colab, make sure that you're using a GPU here, right? Because you're going to train a model, and if you don't use GPU, it will take a long time and it's very annoying. So just make sure we are using GPU. And here is where we choose a base model right from the start. When we're talking about transfer learning in image, the name we use for the base model is feature extractor or feature vector. Why is that? Because these models here on this list, they are exactly like the classification models we've just seen, but they don't have the last layer where they make a decision, right? You have to put one yourself. So what they give you is a representation of an image in the nth space. So it converts one image into an array of 1,000 floats, right? What does those 1,000 floats mean is that similar images technically would be close by in the nth space, right? So if you have two pictures of people and a third picture of a tiger, if you plot this on the nth space, which like it's the 1,000 dimension space, which we cannot imagine, but you can calculate the distance, right? The distance from the people's pictures is smaller than to the tiger picture, right? Because the picture with people is similar in a way, right? So these feature vectors are a way of converting image to a representation in the nth space. From there, you can specialize to explain to your model that, oh, this picture, what you found here is not exactly a person. You found my uncle. So you can start to change to make the model, instead of understanding generic stuff, understanding specific stuff. That's what transfer learning will do. Here, let's choose. This is a very large model. I don't want to use that. I want to use MobileNet v3. This one, v3 small. Let's try this one. And then what we are doing here is same thing, right? We have this map here that gives us model handle and image input size here. And then what we do is we just put them in two variables. Here is the model we are going to use. You can see it here. Same thing, documentation. The data set it was used is the ImageNet as expected. Model architecture is MobileNet v3. This model is interesting because you can see we have a TensorFlow JS version that you can use on a browser. This is JavaScript code here. You can also use this on a mobile device, like on phone. You can see all the metadata about this model and how to use it. We have sample code to use here. There's a sample code to use this model on Android, iOS, Raspberry Pi. And you can see the size here is a 3.93 megabytes. This is the TF Lite version. The regular version, it's a little bit smaller. That's fun. So, but it's usually this model is bigger than the other. But this one is already converted. So if you want to create a image classification app, you could use this model almost directly, right? Let's go back to our code. We've seen the documentation. And now how do we do that? Yeah, MobileNet v3, as you saw in the documentation, it was trained on ImageNet again, 1,000 classes, right? What we're going to do is we are going to use a flowers dataset. Flowers dataset is a dataset of 5 types of flowers: rose, dandelion, tulips, and another 2. With, like, I guess they have maybe 100 or more images of each class in each folder. And that's a very basic data set. People use that to play with machine learning. And we are going to specialize our MobileNet v3 to recognize flowers. So first of all, we download the data set. So here, let's show this code here. There's a flag to do data augmentation. We are not going to do this now, but what is data augmentation? As I mentioned before, sometimes you don't have enough images, right? But machine learning is a field that, for example, when a model learns to look into a dog, it's not like we do that we look into a dog. And if we look the dog from the side, for us, this is still a dog. For a machine learning model, that's not necessarily true, right? So what we can do for each image to make the machine learning understand better is you can get an image of a dog, and you can, for example, tilt it a little bit to one side, tilt to the other side, zoom in, or change a little bit of the lighting on the picture, or you can get different crops of the image, or you can, for example, stretch a little bit, you can do many image transformations, and that will increase your data set by 5-10-fold, depending on how many transformations you do. So just rotation, maybe flip the image like here from here, and you might say, oh, but that doesn't make a difference. Yes, it does make a difference. So machine learning models, they learn a lot of stuff that you are not expecting. So being able to play with the image input can make a huge difference. We are not going to do this on this example specifically. You can, of course, play around as much as you want. TensorFlow gives you all the tools to do pre-processing on these images. And this is used, of course, only for training. Whenever the model is exported for inference, you don't do that anymore, right? It's only for training. And TensorFlow helps you with all of that. And let's do fine tuning. So what's fine tuning? We have our feature vector, our base model. It has all its weights. When you are going to do transfer learning, you have to decide one thing. Do I want to change the original weights of my model, or do I want to use only the base layers I added to the model? If you want to do fine tuning and change all the weights, of course, it won't change much, but these small changes is something that maybe can make your model better, right? I guess I'm going to not do it now, and then we can try later doing it. Let's do like that. So this changing can make your model more accurate, let's say like that, if you change the original weights a little bit. Let's try without it first. And here is we are going to define our model. Remember, Josh mentioned the sequential model. We are going to use sequential model. We are going to have an input layer, which is where the image will come in. The second layer here now is something different. Remember hub.load? Now, since we are composing a model, we can use something hub.keras layer. So it will load the model ready to be part of another model, right? So it can be fine-tuned, like I said before. We're not going to do this at this time exactly. And then we're going to add one dropout layer, and finally a dense layer. This dense layer has n neurons, where n is the number of classes I'm classifying. In our case, we have flowers, right? So it's 5 flowers. So these class names here, so if I do, if we see the size of this, it has to be 5, right? Because we have 5 classes. And if you want to know which classes we're talking about here, right? We can, oh, sorry. If you type correctly, it's better. That's something I learned. So these are the classes we are going to classify: daisy, dandelion, roses, sunflowers, tulips, right? Very basic data set. And now we are going to create our model. Boom. Created our model using MobileNet v3 as the feature vector. And we've added some 2 layers here. As you can see, the final layer here, output is 5 neurons. And the dropout, what does a dropout do? A dropout is a layer that for every epoch of your training, so for example, when you train a model, you go over your image, your data set, at least one time, right? For each, if you want to do like 10 times, your epoch will be 10 epochs. So you're going to go over your data set, a whole data set, 10 times. So 10 epochs. For one epoch is how many times you go over your data set. A dropout layer is a layer that for each epoch, it will pretend some neurons don't exist. Some connections disappear. And it's like, for 20 here, is like 20%, the 0-2 is like 20% of the connections from the keras layer to the dense layer, 20% of them will just not have any value. Why would you do that? Because it looks like you're sabotaging your model, right? You're removing information from it. You do that so your model doesn't rely on specific neurons. It learns to generalize. So a dropout layer is a technique you use to make your model more generic, more able to get images that are not on your data set and do proper inference on them. Otherwise, your model gets overfitted, it learns only your data. And that's not what you want. You want a model that can behave properly on images that it never used, right? Never seen before. That's the main goal of machine learning, right? You don't want to solve only for your data set images. You want to train in others. So a dropout is a technique that helps you with that. Dense layer is what Josh mentioned, is a layer that connects everything to everything. And that's usually the last layer of many models. Now we're going to compile our model. So we define the model structure, the layers. Next thing, you have to define an optimizer and a loss function. What is it? A loss function is given what my model gave me as result, I put an image and I got a result. And what my labels say that the image has, because I have to train a model with data and the labels, right? So given the difference from the labels, proper labels, and the data, the inference that my model did, we need a function that will calculate this distance. And this is what we call the loss function. Here we are calling using categorical cross entropy, which is a very common loss function for this kind of many labels problem. And this will calculate a distance. The process of training a model is basically trying to make this distance as small as possible, because I want my model to make guesses, make inferences that are closer and closer to the proper labels. So, but to get closer, we need to know how far we are. To know how far we are, we need the loss function. And how do I go, now that I know how far I am, how do I move towards the proper answer? That's what an optimizer will do, right? I'm using here the stochastic gradient descent, which the idea is, imagine a surface, and for each point in the surface, I can get the derivative and find to where I should go, where are the increase of the function goes. And that's where I want to go. I want to go to the hills or to the tops. It's kind of same idea, right? So I want to go, and so the stochastic gradient descent will give me a proper direction. So given a loss, I would change all the weights of my model so that directs me proper to a smaller loss. That's why I need an optimizer and a loss, right? Let's compile our model. And now we're going to call the fit method, which has 5 epochs. This usually takes a while. It won't take too much, I guess, because the data set is very small and the model is also small. So that's while it's training there. Let me see if there's a good question here. How does the input layer convert the new images into a right shape? So why it's so there's a question from Charlie. How does the input layer convert the new image into the right shape? So you should have done this before. So the right shape here is 24 by 24 by 3, because we have the 3 channels of color, right? So you have to give the proper size to the model, otherwise it will complain. To do that, there are some array manipulation and so image manipulation functions on TensorFlow that can scale, crop, and do stuff for you for the image so that it has the proper input size. So the input layer will not do magic for you. It will expect one size. You have to respect that one size, otherwise you'll get an error. I guess that's the only question we have. Here, finish train the model. So let's take a look here. I don't know if it will change anything for you. Can you see? Let's close this. We don't need that. Okay. So here what happened is I trained my model for 5 epochs. As I said, 1 epoch means going over the data set, full data set once. The first epoch took 23 seconds and then 888. Why is that? The first time we trained, it had to load all the images to memory, right? And that takes some time, right? There's I/O time there. After that, everything is on cache because the data set is not that big. It fits in memory. That's not always the case, okay? And here you can see that our loss function started at 0.82 and finished at 0.56. So it improved, right? And our accuracy, it's already on 94%. This is okay, I guess, right? 94%. And we have our validation accuracy. So I skipped a step here. It's more theory here. Usually we split our data set in three things: training data, validation data, test data. The training data is what you use to train your model. The validation data is some data that for each batch that you, or each epoch you finish, I don't know if batch or epoch, it will train, it will run your model on the validation data set to see how far you are when applying your model to data it has never seen before. So the validation is for each, I guess it's epoch, you will see, oh, how far am I from data in data that I've never seen? So the important metric here is this one, because this is how your model will behave on data that has never seen before, right? So 91% accuracy here, which is very good, given we didn't do much, right? We didn't code almost anything. And we have the test data set, which is data that you should never put on your, touch your training or validation set. And that's the canary in the mine, right? You use that to test your model on data that you have never seen before. So that's why we have three parts of the data set. That's more theory. I'm pretty sure I'm not the best one to explain that. And here we can see the graphs here, how we can plot all the information that I've just mentioned. This is accuracy and how you can see how it's increasing. And this is loss, how good is decreasing. And now we can do some inference here. Let's see if it goes well. So the label is sunflowers, and it predicted sunflower for this image. Easy as that. And then we can save our model. This is more, I'm going to skip the last part because it's not that important right now. Save the model. And now if we come here, let me see if it's on a temp folder. Sorry, I'm not going to show where to get, how to get there. But you have the model, you can just use it somewhere else, put on a server and play with that, right? And so that's basically it. You did transfer learning, you have a model that's better on your data. While I'm going to make a change here, I'm going to create, do fine tuning. I'm going to recreate my model because you can see fine tuning is here, right? So I need to recreate, compile again. And what I'm going to do now is I'm going to train on another cell. I'm going to call this different, and I'm going to train this again. Right? Let it train for a little bit, and then we can see if the results are better. So the question from Charlie is, why do we have the input layer for this model? That's a very good question. So the input layer here is mainly for when the model is being built here. It knows how to do it better. It knows how to compile parts of the model to being faster. Otherwise, it would have to infer from the first layer. You don't really need all the time to define this, right? That's optional, right? But depending on what you are doing, you might get many mistakes if you don't do it, because if your data is not properly cropped to the proper size, you start to get some weird mistakes in the middle of your training. For example, because you're not enforcing this by a layer, you're enforcing this by what TensorFlow can infer. So it might infer the wrong size. So to avoid this kind of error, we put an input layer. So it's like, no, I know exactly what's input layer. And if my data has any mistakes, I want the training process to find that as soon as possible. If you don't do that, you might end up in the middle of your training a bug, and then it's hard to debug. So it's a good practice to put input layer, but you didn't need, you could do without one, right? Just so we are clear, right? It's just a good practice here. But did I finish? Oh, I finished. Oh, look, I finished already. And you can see here, my validation accuracy without fine tuning, 91%. With fine tuning, 93%. So this is already, we got 2% with one flag, right? So this is kind of a very good thing to know. Let's see if, I hope it doesn't break my model here. Hope it's roses, perfect. So our model is still working. We just added fine tuning and we got a better result. As you can see here on the second model, accuracy is at 99%, right? But that's of course not true, right? It's 99% on the training data set. But in reality, if you try to, oh, is it really 99% on real world data? No, it's not. It's more close to 93%, which is very good, by the way. So this is how you do transfer learning. You can, other things you could try here, I'm not going to do now because I prefer to answer questions or do the NLP part, is you could change this feature vector to any of the other ones. Look how many you have or any others you find and try them and see if you can get better results, or maybe a smaller model, maybe I don't know, whatever you think it's best. So that's one of the powers of TensorFlow Hub. You can easily try other models to do transfer learning. You can see, like, I change one line, one URL, and I can try another model, and that's it. Basically, easy as that. So this is a very powerful tool to have available to you. Questions? When you have, there's a question from Finer. I hope
yes,
I'm saying your... Oh, nice. When you're going to deploy a model, what is the lowest accuracy out of training data set that you are willing to accept? That's a very business related question, and I'll tell you why. Sometimes if your model has a low accuracy, but your model is not doing something critical, that might be acceptable. While if your model is detecting if something is poisonous or not, then you cannot accept a low accuracy. Does it make sense? Sometimes, for example, if I'm doing recommendations for you, I can recommend stuff that's like lower score, like close to, I don't know, 50%, right? Okay. Which is low. I can recommend stuff instead of not showing anything. I just recommend because it's not going to be that much of a damage depending on where we are. While in some situations, oh, is it poisonous or not? Is this mushroom eatable or not? So that depends. So that depends a lot on the business. And for example, a low accuracy in some situations is I can decrease the blur of an image, but not much. But I can decrease a little bit. Okay, that's fine. So that depends on how it's used in the product and how your business is around it. So that's a tricky question. It's not, there's no yes or no answer. Sorry.
Okay, thank you, Gus.
Of course. Any other questions? Oh, there's another question. So fine tuning, perfect, good. Sorry, maybe I didn't explain correctly. I want to find an image. Let's see if I have an image. No, I don't. Sorry. So let's try to explain verbally. Sorry, I would like to show an image of what's happening. But imagine you have you're creating a machine learning model, right? Like we did here. Here, right? Model here. Fine tuning is when I get, for example, here, I have a very large model already, right? When I say keras.layer in a model from Hub, it's hiding a little bit the fact that behind this layer, there's a huge model already, right? There's a lot of, if you look here, there's 1 million parameters there already, right? Remember, Josh showed you a model he created, had like 7,000. Here, this one line is adding 1 million parameters to your model. This 1 million parameters to your model is what we fine tune. So these weights inside this model, they're all frozen. You don't touch them. Unless you say, oh no, I want to fine tune them. I want them to change a little. And then you train your model. So Keras will look into that and say, okay, are they frozen or not? Oh, they're not, so I can change them. Of course, given the momentum and the size of our model, they are not going to change much, right? It's minor changes. So when you find, that's why it's fine-tuned. It's like changing a little bit every weight and making your model more precise, let's say like that. In some situations, you don't want that to happen because your model is already the way it should be. And if you fine tune it, it might overfit, for example, right? So that's why you have to decide. It's also kind of a business plus technical decision here when you want to change the original model a bit or not. That's what's fine tuning. Does it make sense, Gianmarco? Oh, perfect. I have a question for the teacher. If I have time to, I don't have that much time, right? Do I have time to do a little bit of NLP and Hub? Hello? If I have time, I can do. Otherwise, if you want a break, up to you all. Hello?
I can hear you.
Yeah, but should I? Do you want me to do a little bit about NLP and how it connects to Hub? I can, but it might take more. I'm afraid I don't want to destroy your afternoon hearing me all afternoon.
We have time. It's still 12.
Sorry?
We have time till 12.
Okay, I'll do that then. Thank you. Let me find the presentation here. Okay. Nice. Perfect. Okay, let's talk a little bit about NLP and how TensorFlow Hub can help you on that field. But before we get there, let's try to think a little bit. So if you think as humans, right? Text is absurdly important, right? Text is what enables us to get where we are. If we couldn't give the information to our kids and our descendants, it would all die with us. And then we evolve way slower, right? It's not that we can't evolve, but we evolve slower because we cannot pass information forward. So text is absurdly important. And that's something that if you think how we learn it, it's even interesting, right? Because first of all, in school, we learn how to read text, and then we start to write a little bit, and it takes a while for you to do it properly. Maybe I don't do it correctly until there's still a lot of mistakes I make while writing. And in the end, you learn to understand text. So when you have maybe 10 years old, that's when you start to read the text and have a way better understanding. And it takes a while for you to, some books, you take years to understand. So that kind of is how we evolve into text, right? And for humans, it's hard, right? As you can see today, many people can read something and they cannot understand what's written, right? They can, of course, repeat the words, but they cannot extract from their context, meaning, and reasoning and stuff like that, because that is a hard task. When we start to think about computers doing that, that's even harder, right? Because how do you explain to a computer what text means? And this is the field of NLP, natural language processing. The goal is to make computers understand language. Language is spoken, written, all languages, right? And this is very, very hard. And if you think a little bit, how would you get a piece of text and write some code in Python to make that text understandable? How do you do that, right? It's even hard to imagine how to do that. Which kind of tools and libraries do you need? And language has another aspect that's not a text, has another aspect, which is language. For example, I'm from Brazil. I speak Portuguese way better than I speak English. If you write a code to understand English, it will probably not work for Portuguese, right? Because it's a different language. But the idea is the same, right? You use the same tools, Portuguese and English, to express something. And computers have a hard time understanding that. So this is a very tricky problem, and it's absurdly powerful when it can do stuff. So what can NLP do today? Let's give a couple of examples here. And for example, translation, obvious. So if you're using a messaging, sometimes there's a suggestion of a reply of what you can reply to the previous message. There is also, if you use Gmail, I guess it's public, that you can type and it will autocomplete your message. You can just tab and it will autocomplete, which is almost like magic for me. It can do sentiment analysis, which is this message positive or negative? It can do a lot of stuff. And so that's what NLP studies, is how to apply machine learning or computation, computers to understand text and act on text, right? Not only understand it. And in the last couple of years, you've seen many advancements. For example, translation is basically done, most of it over machine learning these days, right? In the past, it wasn't like that because the results were horrible. But later, it's almost a no-brainer because it's a very hard problem to translate stuff, right? By rules. Using rules, it's almost impossible. Given hundreds of languages we have, how do we deal with that? That's very hard. Machine learning came and dealt with all of that. And lately, some new cool stuff happened, right? To make it even more impressive. So here we have 4 images for some models that were really that are the papers, right? Or were released later, not the model itself. I guess none of those models are available to you. But for example, the one on top left is Lambda, which is a model to understand and do dialogues that Google built. And this is the base for, I don't know if you saw a demo where you could talk to Pluto, right? The planet. So Lambda could be Pluto. It can pretend to be Pluto. It can pretend to be a paper airplane, and you can speak to them. And you can see that's a conversation that you can, oh, that really likes I'm talking to a paper airplane, which is weird. But it understands dialogue. It understands text in a huge way. That's huge, right? And if you think, oh, that's not that much, we have the image on the top right, which is from AlphaCode, which was released this week. The paper, not the model. The model is not going to be available, I guess, anytime soon. AlphaCode is it's from DeepMind, right? And you know, DeepMind, they have this sport of destroying nerd sports, right? So they first did AlphaGo, which, well, you know what happened. They did AlphaStar, which played StarCraft better than everyone and me, of course. And now they did AlphaCode, which, given a code competition statement, it can solve the problem. It's not perfect. It's at 44%, close to an average developer, but it's a start, and it's a very good start. And think a little bit, how would you go from a code competition question to a code solution that compiles and solve the problem? Think about it, how far it is, right? Can you imagine if and else to get there? That's when I saw the paper, I said, oh, that's magical. And this is a NLP problem, right? This is a reading, understanding, and coding something in another language. So you can almost think that as a translation, right? You're translating something into code. And when we talk about translating to code, we have other models doing the same thing, like Codex from OpenAI, where you write the specification and it will write the code for you. This is an NLP problem. It's also understanding text and translating to Python, C#, C++, Java, I don't know. So Codex, which is the base of Copilot, I don't know if any of you play with that. It's a tool from GitHub where it auto completes the whole code for you, right? It's like it writes everything for you. And OpenAI also did a model called DAL-E, which what it does is, you can see on the bottom left, you give a sentence and it will draw that for you. The fun thing is, this is not a search. It's creating these images. This is an image that was generated from a query, right? It's not a search result. Of course, if you search for that now, you will get those results created by the model. It didn't learn from images, right? It knows what's an avocado. It knows what's an armchair. And when you ask for them, hey, create an image of that, it will generate an image. Of course, this is also part NLP, right? Understanding the input. And the last one on the right is OpenAI. Also this week, I mentioned this week also, they created a model that can prove theorems. You give the first part of the sentence, prove that if model of x minus 2 equals p, where x less than 2, then x minus p equals 2 minus p. So how do you prove that? So the model learned how to do that, and it even solved some math, 2 problems from a math Olympics competition. And if you think about that, it's amazing, right? This is huge. Again, the model is not perfect, but it's a start, and it's all based on language, based on text, understanding text, converting to something. This is almost like magic for me, right? But the problem we have is, how do you put text on a model? Because a model is basically a very big math equation, right? It's like y equals w times x plus b, right? A times x plus b. This is a math equation. What a model is it has a lot of values for a and for b, right? Because this equation is very simple, but if you have x1, x2, x3, x a billion, you have one parameter for each one of those. This is what a model is, kind of like a very simplification. It doesn't know how to do with text. How do you convert text to numbers? And this is one of the main things about NLP, is how do you go from text to numbers? And so you have, how do you do that? You can think about many ways of doing that, right? You can define a way right now. Let's try something. For example, I can define for each letter, I give a number. So these numbers would be for the word listen. But if I write the word silent, it has the same letters in just a different order, just same numbers in a different order. And the meaning is completely the opposite. So how do I represent words and letters as numbers in a way that it doesn't lose context or meaning, right? Because that's what happened here. I would be able, for example, to give one number per word, but how does, if I have another sentence like I love cat, my cat, I give number 5. What does it tell the computer, right? What kind of context and meaning are on those numbers? And that's where we start to learn something that is called language embeddings. Language embeddings is a way to represent text as a vector of numbers. And remember I mentioned feature vector, right? So you get an image and you convert to an array of floats. A language embedding is you get text and you convert to an array of floats, which is kind of plotting these words, sentences in the nth dimension, right? Like you see there. This is a tool on projector.tensorflow.org that you can put your language embedding and it will show for you in 3-dimensional. That's all we can see, right? Usually language embeddings have maybe thousands of dimensions. It will just show 3. And what does it mean is a language embedding is good when similar words are close to each other in the space. So for example, cat and dog would be close to each other than table, for example, right? And these words being close to each other makes a huge difference, right? And language embeddings try to do that in a way that you can use that information to understand text, to understand that you're translating A to B and the meaning is the same, to understand that a sentence is positive or negative, to understand how to find the main point of the sentence, all kinds of things. So language embeddings is a key part of NLP, key part. The problem is training a language embedding can take weeks or a month and a lot of data, like all the internet, for training a language embed, and you don't have access to that. Only big companies have access to that. And even if you do that, it's harder than just using the data as is, because there are many aspects of bias. For example, imagine if I train my language model with the Twitter data. Imagine how much hate there's going to be on my language embedding, or bias, or prejudice, or it's not easy. It's very hard. So training a language embedding, it's a challenge by itself, right? It's there's all the other NLP problems. They all depend on language embeddings. Language embedding is a problem by itself. And why am I talking about this? Because TensorFlow Hub has a lot of language embeddings for you to try directly. It has in many languages, many sizes, many techniques, so that you can easily try. And let's take a look on one quick example. I'm not going to go into code now because we don't have enough time. So for example, here is one basic language embedding, NNLM. What's written there is I'm loading this model from Hub. It has 50 dimensions. So for each sentence, it will convert to an array with 50 floats, right? And so if I give you these two sentences here, it will return to me two arrays of 50 floats each. And those are the embeddings of my sentence. And I can use this to do sentiment analysis, for example. I can say both sentences are kind of positive, right? The one today, the sky is blue, depends. But you can train any models based on you receive a text, convert to embeddings, and now your model do some magic on it, right? Do some dense layers, dropouts, and stuff like that. So if I want to do fine tuning, same thing. I can do Keras layer, and here's a model that will do exactly that. Here's a very simple example of how we can use a model from Hub to do sentiment analysis. There's that URL on the bottom. You can just copy. I'll copy on the chat later, and you can do exactly that code in Collab, right? So what's happening here? Loading the layer, the embedding layer, and creating a sequential model, and following up from someone asked, why do I need the input layer somewhere, right? Here you can see I'm not defining input layer, right? Doesn't matter because I accept any size of string here. So for this case specifically, I'm not even defining input layer because I'm not putting restrictions. And then I put a dense layer and another dense layer with size 1. Size 1 because the result of sentiment analysis is a number from 0 to 1, I guess. Sigmoid from 0 to 1, where 0 is negative, most negative, 1 is most positive. So the closer you are to 1, the more positive the sentence is, right? And I train a data set. This is using EMDB data sets for reviews. So you can follow that URL I'll paste for you. This will train you a sentiment analysis. Easy as that. As you can see, text is not the problem. You just use the Keras layer and you get like embeddings for free, and you just train your model as if it was just numbers. Easy as that. And if you want to get better results, you can just change the embedding to a better one, right? To a bigger one. This one, if you can see, it's using 128 dimensions instead of 50 that I showed in the previous slide. And easy as that, right? But I'm going to hush a little bit here. But that embedding, this NNLM is good. It's okay, but it's not amazing. Let's say like that, right? One thing is lately when Josh mentioned transformers, right? When transformers was invented, it was 2000. I forgot. Lately, 17, 18, 19, something like that. Transformers were created, the architecture, and one of the main models that came from that architecture is the BERT models, right? BERT models is an implementation of transformers that works as a language embedding. And why it's so powerful? It's because it can entail context better than all other language embeddings. So the idea is that you can give text to BERT, it will convert to numbers, and those numbers contain all the context you need. So if you go back to those examples, the AlphaCode, Lambda, and many others, one of the base things they use is a BERT model. So they do a lot of stuff, but for language embedding, they have the BERT model there, right? So BERT is for bidirectional encoder representation of transformers. And the idea is that it learns from, you give some data that you tag by hand, and the rest it learns kind of taking a data and masking part of it and trying to predict what should go there. So imagine you have a sentence, I love my dog is a bad one. No, let's go to the sky is blue today. So the process of training is it will get the sky is cover blue and keep today, and part of the training will be for the model to figure out what word is missing from the sentence, right? And you kind of know the answer because you've got the original sentence first. So you can create a lot of training data with only some sentences, right? And that's what it did with a huge data set. Still, as of today, it's still state-of-the-art model, and it's using the Google search. So when you type something on Google search, there is a BERT model that's trying to help find the best results for you, right? Imagine sometimes you type something out of order or with wrong letters, or you type something that doesn't make sense. Well, there's a BERT model that's helping you there. And that's why you get some amazing results. And on Hub, we have many BERT models available, many. This list is old, there's more. There's BERT models for all kinds of things, for specific corpus of data, for example, medical data, for lawyers, for more technical. We have BERT models that are smaller in parameters, so they are faster. Of course, they lose accuracy sometimes. Sorry, you have also models that are more that have different training parameters that have better results. And there's many BERT models, kinds of BERT models, and they're all available on Hub, and you can use them all the same way, right? There's mobile BERT, of course, and the same way. And the problem with BERT models at first is that they were trained using TPU. When you use TPU, you cannot do some string related stuff because TPU is a coprocessor. It's not like a GPU that has a very rich set of operations. It has a limited set of operations to deal only with math. Math doesn't have text, right? Cannot understand text. So when we train BERT models, we don't give them text directly. We give them other representations. And to do that, to do training most of the BERT models, usually you would use some tokenization, which converted some words to text, to numbers. You do a lot of magic. And that was one of the problems of BERT inputs in the past, right? And that's tricky at most, right? But we changed that, right? We improved that for TensorFlow Hub. So we have something called preprocess for BERT, which is another model on Hub that gets text and converts to the proper BERT input that you need. You don't need to think about anything. You give text to the preprocessed model, the model converts, and you give directly to BERT. And that just works. Easy as that. You don't need to convert. And that makes using models so much easier. So you can see here, for example, we have the encoder, which is a basic BERT there, a small BERT, and we have the preprocessed model. Where's the code? I want to show all the code. Here it is. So this is how we create a model. We created another sentiment analysis here. Same thing. We created both layers. Encoder, we put a dropout of 10%, dense, train, and compile and train. This will do the same thing that we did with the NNLM, but using a BERT model with the pre-processing layer. As you can see, it's very similar. Of course, there are some details there for you to deal with BERT models. But the difference is that a BERT model is way more powerful than the NNLM language model. So if you're doing something state-of-the-art or with more complex data, text data, you want a better language embedding, and all the BERT models are available to you. If you go to this URL here, there is some examples on tf.org. TensorFlow.org/text has many examples of code on Colab that you can play with BERT. So if you're into NLP, I strongly suggest to take a look and play with them. But we don't have time to do it now. Sorry for that. Sorry for this. And so TensorFlow Hub is here to help you. Thank you very much. Almost on time.